Let me hit you with a number that genuinely stopped me in my tracks. The most powerful supercomputer on the planet in 2024, this beast called Frontier, fills a room about the size of 2 basketball courts. It peaks at roughly 1.7 exaflops. Researchers now think they can do 20 exaflops, more than 10 times that in something the size of a shoebox. A shoebox. On your desk. There's a catch, of course, and we'll get there, but the bigger story is that the whole 50-year game of computing might be about the flip. Not get a bit faster. Flip. We've been writing silicon since before most of us were even born, and for the first time it really looks like something else could take the wheel. So today, I want to walk you through superconducting computing, what it is, why it suddenly matters, and whether I actually buy the hype. Quick spoiler, I kinda do, so let's get into it. Here's the thing nobody really spells out for you. For decades, computers got better because we kept shrinking transistors. That's Moore's law, and you've heard the name. Smaller transistors, more of them per chip, more power. It's simple, and it worked beautifully for about 50 years. But that road is quietly ending, and the reason is sneaky. The problem isn't that we can't calculate fast enough. It's moving the data around. Every time electricity rounds down a wire on a chip, it hits resistance. Resistance makes heat, and when you're shuffling trillions of bits across a chip, then across a whole data center, the heat turns into the main thing you're fighting. And it's getting worse fast because of AI. One query to a large language model burns somewhere around 2.9 watt-hours of electricity. That's roughly 10 times what an old Google search used to cost. And some estimates put a single ChatGPT-style query at around 2.9 watt-hours versus about 0.3 watt-hours for a traditional search. Now, multiply that by hundreds of millions of people, then add a new wave of AI agents, systems that don't just answer once, but search, reason, call tools, and talk to each other across dozens of steps. Every step is more data moving, more wires, more heat. The big picture numbers are honestly a little scary. Global data centers ate up around 415 terawatt-hours of electricity in 2024, which is about 1.5% of all the power humanity makes. And the IEA expects that to more than double by 2030 to around 945 terawatt-hours, roughly Japan's entire yearly use. In the US alone, Dell-wide figures power demand from AI data centers could grow more than 30-fold by 2035, hitting 123 gigawatts, up from just 4 in 2024. We're now building data centers that need their own dedicated power. Gas plants, even nuclear reactors bolted to the side. Deals between data center operations and small modular nuclear projects jumped from 25 gigawatts at the end of 2024 to 45 gigawatts today. So when I say silicon is running out of road, I don't mean it'll stop working. I mean we're slamming into a wall where the energy cost of moving information is becoming the bottleneck for the whole field. And you can't really shrink your way out of a heat problem. You need different physics. This is where superconductors walk in, and honestly, this is the part that made me fall for the topic. Cool certain materials down far enough, and I mean far enough, down to around 4 Kelvin, which is about 296 degrees Celsius in the minus, colder than deep space, by the way, and something almost unbelievable happens. The electrical resistance doesn't just drop, it vanishes completely. Zero. Electricity flows through them with literally no loss. No resistance means no heat from moving data. The giant problem we just spent 5 minutes on? Gone, at least in theory. And that's not a nice little improvement. That's tearing up the rulebook. But you can't really build a computer out of zero resistance wires alone, because computers need switches, things that flip between states. And here's the clever bit. Instead of transistors, these chips use something called a Josephson junction. Picture a tiny sandwich, 2 layers of superconductor with an ultra-thin slice of non-superconducting stuff in the middle. Imec showed showed these off as one of the 3 core building blocks of supercomputing digital circuit, alongside the interconnects and capacitors. So, how do you actually compute with one of these? This part is wild. Instead of pushing the voltage levels around like a normal chip, superconducting logic uses tiny quantized pulses of magnetic pulse, single flux quanta, the smallest possible packet of magnetic field the universe will hand you. 1 quantum of magnetic flux stands in for a bit. A pulse means 1, no pulse means 0. The information rides along these little pulses zipping through the circuit. And the payoff is jaw-dropping on 2 fronts. First, energy. When a Josephson junction flips, it dumps only about 2 times 10 to the minus 20 joules in a picosecond. SVQ switching happens in roughly a picosecond with energy around 10 to the minus 19 joules per switch. Those numbers are so small that they almost stop meaning anything. We're talking thousands of times less energy per operation than silicon. Second, speed. SVQ circuits have been demonstrated running past 120 GHz. Your laptop CPU, it runs at only 2 to 5 GHz. So that's 20 to 100 times faster while sipping a fraction of the power. When I first read those figures, I assumed I misread a unit somewhere, but nope, I didn't. Now, I need to clear up something I see constantly because it trips up a lot of smart people. This is not quantum computing. I know, Josephson junctions near absolute zero. It sounds identical, but it's a totally different animal. Quantum computers use qubits, a superposition entanglement, exotic states that need brand new algorithms and a whole new way of programming. They're incredible for a narrow set of problems and useless for most others, and the software basically has to be reinvented from the scratch. Superconducting digital computing is a different thing. It does plain old classic computation, 1s and 0s, the same logic your phone runs, just on wildly better hardware. It's pegged as one of the most practical paths for the next generation of computers thanks to its ultra-fast, low-power performance versus regular CMOS. And to me, that's the killer feature. It means you can potentially run existing software on it. You are not begging the entire world to rewrite everything. You're swapping the engine, not redesigning how you drive. That compatibility is exactly why I think this has a real shot when some flashier ideas simply don't. Okay, here's the $1 million question. If this is so great, why isn't it everywhere? Well, because for years the materials were a nightmare to manufacture. Old superconducting circuits used pure niobium, and niobium junctions ran into serious scaling walls. Limited current densities, devices that couldn't shrink below about 250 nanometers, and a low thermal budget that kept them out of standard chip making. Enter Imec, a world-leading nanoelectrics hub in Belgium, and the reason I'm making this video right now. They made a swap that sounds boring, but is a huge deal, from niobium to niobium titanium nitride, a material that plays way nicer with normal chip fabrication. Turns out niobium titanium nitride can stay superconductive and get built into logic and memory circuits using amorphous silicon as the thin barrier inside the junction and can be mass-produced with existing chip fabrication process. That last part, existing chip fabrication processes, is the whole ballgame. Using these new junction stacks on a 300mm wafer, they hit current densities around 2 to 3 milliamps per square micron and junctions as small as 210 nanometers. And this is current stuff. At IEDM 2025, Imec showed off advances in its niobium titanium nitride platform. Higher junction densities, better reliability, stronger superconducting properties, and the target they're chasing? Superconducting digital tech that delivers up to 100 times the energy efficiency and 10 to 100 times the performance of today's CMOS processors. 100 times more efficient. That's not a tweak. That's the kind of leap that could take a data center the size of a football field, drawing the power of a small city, and genuinely shrink it toward that shoebox we opened with. Alright, I promised you a catch, and here it is. To make any of this work, you gotta keep the whole thing at around 4 Kelvin, colder than space, and that needs specialized fridges called cryostats, and these aren't your kitchen mini fridge. That shoebox-sized computer also has to sit inside a rack-sized insulated cylinder cooled by a refrigerator about the size of 3 computer racks. So, you save a mountain of energy on the computing itself, but you spend that energy and money on the cooling, and that's the real question hanging over the whole thing. Does the math actually work out? And for your laptop? Obviously not, but nobody's strapping a cryostat to a MacBook. But for a giant AI data center that already needs its own power plant, where you're cooling at massive scale and the gains are enormous, that's exactly the case where dragging things down near absolute zero might genuinely pay off. There are other hurdles too. Design tools for these circuits have lagged for years, and SVQ circuits have quirks, like fan-out limits and sensitivity to magnetic fields, that make big designs very tricky. This isn't shipping next year, and I want to be straight with you about that. So here's where I land, and I want to know if you're with me. I think superconducting computing is one of the most slept-on stories in tech right now. Everyone's fixated on quantum, which is still years from being broadly useful, and meanwhile the quieter technology does classical computing, the stuff we use every single day, potentially 100 times more efficiently, and it fits the chip factories we already have. The fact that Imec is hitting these milestones in standard 300mm wafers tells me serious players think it's real. Imec even confirmed partnership talks around its superconducting program are underway. So will it replace the silicon in your phone? No, and it really doesn't have to. But for the giant power-hungry data centers driving the AI boom, the ones literally reshaping our power grid, a beyond silicon future built on changing the physics instead of just shrinking transistors feels like sci-fi every year, and I find that genuinely exciting.